I'm Kezia Sharon Christopher, and my project is to detect the neurometabolic features from magnetic resonance spectroscopy of basal and lesion brains using feature learning algorithms. The problem that we are addressing in this project is that the inflammatory markers obtained from an MRI image have no molecular specificity. For example, in these three images, it is clear that there are lesions or inflammations in the brain, but we don't know what lesion it is. It could be edema, it could be MS or Alzheimer's disease. The inflammation could mean anything. A solution for this is magnetic resonance spectroscopy or MRS. MRS is a non-invasive imaging tool that helps detect the changes in the metabolites in the brain, which can be used as biomarkers between basal function and pathologies like MS or tumors in the brain. The spectra that you see here on the left is an NMR spectra on a ppm scale. Here, each metabolite peak appears at a specific ppm, that is, it has a specific ppm value. For example, the peak at 4.8 ppm is water, the peak at 2 ppm is NAA, and each of these metabolites reflects a specific cellular and biochemical process. For example, NAA is a neuronal marker, so decrease in NAA means neural integrity has been affected, like in the case of MS lesions. However, in the MR spectra, even though there are thousands of data points, only a handful of these peaks and metabolites are identified. We believe that there is more information other than these known metabolites that change between an injured and a non-injured brain. Machine learning is used in image analysis to detect recurring features in complex data, and MRS data is an ideal application for machine learning. In this project, we will be using learning algorithms to detect neurometabolic changes to analyze the whole MR spectra, detecting statistically significant features of basal and lesion brains. MRS data was collected before injury, then the injury was caused, and the data was collected 24 hours, 48 hours, and 7 days after injury. This would help us track the changes in the metabolites in the brain at different time points before and after injury. After processing the data, principal component analysis or PCA is applied to the data set. PCA helps in simplifying high-dimensional data while retaining the patterns and the trends. While we cannot know the chemical species of every peak involved, the learning method offers a statistically rigorous analysis that makes use of all the molecular information made available by MRS. Developing learned signatures into clinically useful biomarkers would bring more understanding to human studies and diagnosis and a groundbreaking advancement in the field of molecular imaging. Thank you.